Hello, everyone. We are Team Scopen. We will give our Capstone project right now. So before get started, let's introduce ourselves.
Hi, I'm Byron Aguilar. I was the team leader of the project. I also helped develop some parts of it, such as the analog front end and the firmware design.
Hello, everyone. I'm Boning. Basically, I'm in charge of system design, board layout, firmware, software, and board assembly.
Hello, everyone. I'm Caesar. I'm in charge of AFE design, power management, and firmware for the DAC interface.
Okay, first, we want to give you guys a little bit background why we want to build such a project. So I guess you guys all have the experience of using an oscilloscope in the past 4 years. I'm not sure about you guys' experience of using an oscilloscope, but for me, I think using an oscilloscope is not very easy. First, because we always need to go to the lab to access the device, which is kind of inconvenient, especially during the COVID-19 situation. It's getting harder even. The second thing is oscilloscope usually take a lot of space on my table. So, using an oscilloscope with my laptop, usually I don't have enough space for something else. The third thing is if you want to get one at your home, if you're not a hardcore developer, like a hardcore engineer, probably you will not, because that's super expensive and also kind of inconvenient. So we are thinking whether we can solve this problem. And the first question we ask us is, for students and hobbyists, do we really need a huge and expensive one? What are the key features we actually need for students, right? So our answer toward this, we believe there are 4 important things. First, it should be able to detect waveform. After all, that's an oscilloscope. If you can't do that, that's not, right? Second, it should be portable. What do we mean portable is, what if you can put that in your pocket, in a folder, in a bag? That would be so convenient. You don't need to go to school anymore. Even during COVID-19, you can debug that at your home. The third thing, we want it to be intuitive. What do we mean intuitive? Because we believe 90% of the features in oscilloscope, in the real professional oscilloscope, we are actually not using it. For our personal project, the frequency are usually pretty low, and a lot of features actually just be wasted. So the fourth thing we believe is the most important thing is it should be affordable. For students, you don't want to spend $700 on a device and just use it once or twice per year. So eventually, we want to build a device that converts your workbench from the top to the bottom. Our solution to the problem we proposed is Scopen, a wireless oscilloscope, the power of an oscilloscope in a pen. So before going into the technical details, let's watch a demo video to get familiar with what it's capable of.
Yeah, our project structure branches out into 4 categories. We have hardware design, where we can find the analog front end and various systems. The firmware design encompasses the waveform sampling method we developed and thread manager. Software design handles communication between Scopen and the user's device. And the industrial design focuses on the physical appearance of our product. Expanding on the hardware design, the analog front end handles the initial input and converts it to an acceptable differential signal. The STM32 microcontroller is responsible for sampling this differential signal, sending the data to an external memory, and later moving the data to the Wi-Fi module. As mentioned before, the AFE's purpose is to handle the initial analog signal and massage it enough to be sampled by the ADCs. In order to be able to handle a wide variety of voltage signals and amplitudes, we needed a robust design that can ensure everything is accounted for. The input first goes through a stage in which it will be attenuated or not. If it is attenuated, the signal's amplitude is heavily decreased, and this is how we are able to measure the larger signals. After the attenuation stage, the signal goes through an amplifying stage that increases the signal's amplitude to fit the max sampling range of the ADC. This way, we take advantage of the ADC's full capabilities. The last stage is for the input to be converted from a single-ended signal into a differential one. The ADCs are able to measure single-ended signals, but in order to smooth out potential disturbances, having a differential signal works best. A few of the challenges we faced for the AFE design are the following. We needed to make sure that the impedance of one stage wouldn't distort our signal, so we selected components with high input impedances and placed buffers in between stages to ensure our stages are isolated from one another. Designing the gain stage was quite difficult as well. We knew we needed multiple gain settings to account for the various signals. Our solution was to use a VGA or variable gain amplifier, but finding a VGA that provided a variety of gain values was quite difficult, but we ultimately found one that was perfect for the task, where we could control the gain using the DAC found in the STM32.
The main purpose of our hardware system is to sample and send data to the user quickly. We also wanted to implement a feature to change oscilloscope settings with simple touch gestures from the pen. To achieve the sampling, we needed fast ADCs. This is taken care of by the STM32 G4 microcontroller. Once an oscilloscope obtains data points, often it obtains a large amount of data points. So this data has to be buffered into external memory before being sent out through Wi-Fi. Lastly, to implement our wireless feature, we needed a Wi-Fi module. In this case, we chose the ESP32 Pico so that we could implement that feature. Some of the challenges we faced with designing this system was part selection. In particular, for the microcontroller, we needed a part that had a small package but had fast ADCs. Unfortunately, not many microcontrollers on the market have this combination of features. So to compromise, we chose a microcontroller with 4 medium-speed ADCs that could be combined together to increase our sampling rate. For the memory selection, we had to choose a part that had big enough storage, had a small package, but still was easy to solder. Luckily, we found the IS6 static RAM module, which fit our criteria. Now you may notice the theme of our challenges and our part selection is that we wanted something small. We needed something small. This is because our goal was to fit this system into the form factor of a pen. That is why our system had to be compact, and that is why we designed our 6-layer board. On the screen right now, you should see the 6 layers that we used. As you can see, the traces are small and the routing is compact. This is all to fit everything into one single PCB. And the 3D render here, you can see like all the components, how they fit nice and compact onto the board. Overall, the length is 2.45 inches in length and 0.73 inches in width. To put this in perspective, this board is no bigger than your average stick of gum, so it's quite small. But to achieve this size, we couldn't just rely on one side of the board. We also had to place components on the other side of the board. So on the other side of the board, we also have more passives and ICs where to incorporate our entire hardware system into one single small PCB that can fit inside a pen. And then the end result was this small board, and we were happy with the end result, and it fit our project goals perfectly.
Okay, so next I'll talk about firmware design. Basically, the firmware can be divided into 2 parts. The first part is STM32G4. That's the core controller of our system, basically handling all of the peripherals like touch sensor, battery management, handle the sampling. The other part is the ESP32. Basically, that's a Wi-Fi controller. This controller functions as the bridge between the core controller and our software. We will talk about that later. So the first thing I want to show you guys is the firmware architecture of our project. Basically, left and right, there are two parts. Let's look at the left first. From the bottom, that's the lowest level of our software, basically, firmware, I should say. So our project, the STM32G4 is a Cortex M4 architecture controller. This is important because it's free RTOS. We will talk about it later. Actually, use this part. So also for the driver level, we use a lot of STM32 Hall drivers library, including SRAM, ADC, SPI, DAC, a lot of things. But some peripherals, for example, a touch sensor requires special features. For example, I2C restart feature. But this feature is not enabled by the STM32 Hall library. So the way we solve that, we actually develop our own library based on STM32LL library. LL stands for low level. It's actually a wrapper for all of the registers. So that's basically the bottom level, the driver level. The second layer is basically the peripheral layer, we call it. So basically, we can see the touch sensor, we can see an analog front end, we can see battery management. And another thing that across this layer is a free RTOS. RTOS means real-time operating system. The reason we need that is because we want to manage different threads. And on the top layer, the highest one, you can see we are running actually 5 threads in the same time. So 3 of them are handling a data transmission, sending and receiving. The other 2 are handling internal events. For example, if you send something to the controller, you need to be able to run the command. Another thing is handling the user input. So on the right-hand side, that's the ESP part. ESP, we actually developed the ESP using Arduino. So the stack looks a little bit easier, but actually that's not the case when you really do the development work. We're going to talk about that. So several challenges we are facing at this stage. The first challenge is how can we make sure the ADC sampled in equal space time span? That's super hard. You probably say, okay, how about set a timer and use interrupt? Every time you trigger the interrupt, inside the interrupt, you call the ADC. You say, okay, start sampling. But there's a problem. We need to consider about the context switching time of the interrupt. Even though it's super fast, but that time is actually unpredictable. Because for example, you're running a routine right now and the interrupt happened, you need to jump to another routine. That part of time should be considered. So our solution toward this problem is we are using the high resolution timer on our system. How does this work? You can actually set several compare values to the high resolution timer. And when the counter is running, it will keep comparing to the compare value. If it's the same as the compare value, it will trigger something. For our case, we will trigger the ADC sampling. So the way how it works, we set a period for the high resolution timer, divide the period by 4, so that we can make sure the ADC are triggered in equal space time span. So that's the first part. After the ADC is done sampling, it will tell the CPU, basically say, hey, dude, I'm done. What are you gonna do? Whatever. You're gonna handle this, right? So the CPU will take over right now and tell the DMA to migrate the data from the ADC to external memory. The reason that we are not asking the CPU to handle the data transmission, because this will take a lot of CPU time. But CPU can see with the help of DMA, CPU can simply say, okay, help me move the data from here to here, and I will now take care of the rest. Just tell me when you're done. So in this way, we are offloading the CPU time, basically. Use it for a lot of other things. That's the first part. Second challenge is the thread management. Like I mentioned, we are running 5 things together in the same time. How can that be possible on a controller only have 1 single core? That's why we use RTOS. RTOS is an operating system, so it manages the threads for us. But even though we can run 5 things together in the same time, there are still other problems. For example, when the data sending and command sending thread are trying to send things in the same time, what's that going to happen? For example, they're all trying to access the SPI. Is there going to be a problem? The answer is yes. There's going to be a race condition. And if race condition happen, probably it will corrupt the data or probably it will crash the system. That's definitely not what we want. So how could we solve that? We actually use a semaphore. Semaphore actually functions like a lock. So every time you are trying to send something, you lock the semaphore. So if another thread is also coming right now, say I want to send something to the spy, it will also try to lock. But if the spy is already locked, it will wait for a while and come back again to check whether it's unlocked. That's the idea. Another thing we would like to mention for inter-thread communication, we are actually using a queue. So with the queue, we also have the race condition issue. The way we solve that also use semaphore. But the interesting part here is we use two semaphore. The reason is semaphore has an associated counter inside. So we can actually use the counter to represent how many empty slots we have, how many available commands we need to send. In that way, there are two semaphore, solve the race condition, and also make the code to be manageable, clean, and structured. So for the ESP challenge, Byron can talk about that.
Right. So the goal of our firmware in this stage is to create an interface between the user GUI and the microcontroller. And in this process, the ESP32 Wi-Fi module had to be as transparent as possible, meaning that it should only send the data from one end of the chain to the other without introducing any delays overhead. This was difficult to do because we had to implement various communication protocols, create our own communication format, and make sure that the upstream link and the downstream link were as fast and reliable as possible. Now I'll present how our communication worked. So first, the user connects to the Scopen wireless network. After that is done, the user interface sends a scan message, which the Scopen picks up and replies with its own network information. Using this network information, the user interface connects to the Scopen's TCP sockets, and then the user can start sending commands back and forth. So for example, to start sampling, the user interface sends a command through the TCP socket to the Wi-Fi module, and this command is forwarded via UART interface to the microcontroller. Now, we wanted our own communication format to make this as clean as possible. So first, between each communication, a header is sent. And in this header, it contains the data size and the data type. And once this header is received by the receiver sends an acknowledge back to the sender so the sender can send the remaining data forward. So once this, for example, this sample start command is received by the microcontroller begins sampling data and sending it upward through an SPI interface to the Wi-Fi module. And once the Wi-Fi module receives it, it just forwards it via another TCP socket upstream to the user interface. And in the user interface, it processes the data and displays it on the screen.
Okay, next we're gonna talk about the software design. Software design, we actually have two parts, but we will talk about only one. We're actually developing the desktop software and Android software together. But as Android software, we haven't tested it, so we will not mention too much here. So the only thing that is important about software design, I think, is the architecture. Even though there are a lot of details here, different class names, probably you can see that it's fine, it's not important. The only takeaway here is understand that there are three layers. There are three layers because we are trying to follow the model view controller design pattern, which makes our code more clean and manageable. So at the bottom, that's the model layer. Model layer basically handles the data structure, underlying data structure, and a low-level communication logic. Low-level logic is, for example, the communication, command parsing. So in the layer in between, the red color one, that's the controller layer. Controller layer is just like we can say the bridge between the bottom and top. So on the top, that's the GUI layer, or say Viv layer. This layer handles everything you can see on the screen, every buttons, all the knobs. We actually use a super low-level swing library to draw out everything, to draw all the knobs line by line, because we want to make it look good. So another thing this layer handles is also the user input. When the user click a button, the logic here, the event actually triggered here. Another thing about software we want to mention is from the signal propagation perspective, when you receive some data, when you receive some command from the pin, it actually triggers an event at the bottom layer, and the signal propagates toward the top. If user clicks something on the software, the events actually happen on the top layer, and the signal propagates from the to the bottom. The last thing I want to mention is there are two squares that are not colored. You can see right color is sort of wireframe. These two are not classes. These two are actually interface. We designed the interface because we want to enable the callback functions, and we also want to make our code to be more clean, more organized. Basically, that's the architecture part of our software. Next, I want to show you guys the interface. So you click scan, you can find the available pin in the network, connect to it, and you can click start. So here you are sampling the waveform. You can change the voltage division. You can change the time division. So basically, that's the interface of our software. Super simple, intuitive, with a sexy dark theme, which is kind of popular in recent years. So I would say that's really, really good. Next thing we want to show you guys, I guess Caesar going to talk about the industrial design.
Yeah, so the industrial design encompasses how we design the body shell for our product using Fusion 360 software. The biggest challenge was our lack of experience with 3D modeling. So creating a design that is both functional and appealing was quite difficult. And because we are 3D printing the shell, we had to take into account the durability of the material and make sure all the components fit inside the casing. We had to fit the PCB board, the embedded touch sensor board, the battery, and the steel tip while creating foundations for all of these components to secure them in place. Overall, we are extremely happy with the design, and this next video showcases our product.
Wait, actually, I can now switch to the next one. Okay. So I'll make a summary about our product. It supports 20 volt peak-to-peak voltage range, total length 5.9 inches. When you hold it just like a marker in your hand. It also supports micro USB charging with the lithium-ion battery inside, which enables the portability, right? So the sampling, the input signal bandwidth, that's 5 megahertz. I would say it's definitely not high, but definitely enough for you guys. Trust me, for students, it's definitely enough for us. For most our personal project, it's probably the frequency even lower than 1 megahertz. Also, it has a touchpad on the pin, so you can interact with the pin, change the parameters, change the voltage division, time division easily, intuitively. Next, I want to compare the price with different products. So our pen only spent $120 in total for making one. By the way, that's why I mentioned, the reason I mentioned by making one is because if you are trying to sell this product, make this to be a massive production, it'll be way cheaper than this. So comparing our product, we can see the other two. Digilin, you guys are familiar. We all use this in our EC10 series class. It's portable, yes, but it's not wireless. It's still not portable enough, not convenient enough. The other one is WS2000. This one, we actually find it before rebuilding our product. But the thing is, they are super expensive, $300. And to be honest, if considering about spending $300 buying a pin-shaped oscilloscope without a good performance, I'd rather buy a Switch with Animal Crossing probably. It'll be way worth it because the pin-shaped Scopen is actually, their performance a little bit faster than ours, but actually not that fast. If you're a professional level user, you will not consider about that, probably spending a little bit more to buy a professional oscilloscope. So till right now, we covered up all of the details of our product. Next, I think Caesar, I think Byron gonna do the conclusion.
Yeah, so to conclude, I just want to give special thanks to the people who helped us with our project, to our sponsors, Qualcomm, Veritech, and the UCSB College of Engineering. Also, special thanks to Professor Yoga, Adi, and Kyle for their guidance throughout this journey. Also, special thanks to Leo for helping us film our demo video, and Jeff, who helped develop the Android application. But as Boning said, we couldn't fully test this, so we didn't include it in the presentation, but we still wanted to give an acknowledgement to his contribution. So are there any questions?
Are you guys selling any of these?
Not yet, not yet.
Not yet,
We still
not
have to
yet.
do
We are thinking
let's
about
move on
it.
a few bugs. Yeah.
Yeah.
Cool. What was the hardest part regarding the hardware design?
Hard part, I guess, is divided into two parts. For system part, because I work on the system part a lot. I guess the hardest thing is how to pack everything into such a small board. Especially, we also need to consider about some high speed what I call high speed transmission, high speed wires. Like for example, when you sample an ADC, you need to make them to be a differential pair. That's why we also use a differential amplifier in the first stage, actually. For AFE part, I guess Byron and Cedar can talk more about that.
Yeah, so for the AFE, like we have to make sure that there was like it could input a large amount of arbitrary waveforms as well as have low noise. So these were a lot of challenges that sometimes we overlooked, sometimes we couldn't accommodate for. So improving on that would be something that we would do in the next if we had more time.
Right.